It's a talk on holographic DC conductivity in 3D gravity. So I'll let you know after 10 minutes, Kristiansen.
Yes. Thank you very much. I am very happy to be here and being able to show my work with you. This work was done with Marcela Cárdenas, Hernán González, Kristiansen Lara, that's me, and Miguel Pino. And the title of this work is Holographic DC Current in Three-Dimensional Gravity. So table of contents, there's a motivation, an objective. We're going to study the model. Then we are going to study a two-terminal conductance associated to this model. And then we are going to see the same result, but from the perspective of ADS3 gravity. So let me begin with the motivation of this work. There is a specific symmetry that appears in condensed matter system, and its name is Lifshitz scaling or anisotropic scaling. And the scaling, you can see it here, where lambda is some number and z is some integer. And the Lifshitz symmetry has been studied in different references. And we want to study a simple invariant model under Lifshitz scaling, that is the anisotropic chiral boson. So let me see a second motivation, but given from 2+1 general relativity in the context of the work of J.D. Brown and Mark Henault, who proved that ADS3 general relativity with some particular choice of boundary conditions exhibits asymptotic conformal symmetry. This is a very interesting result because general relativity is a trivial theory from the bulk perspective. Namely, the theory has no propagating degrees of freedom. However, the work of Cossert, Henault, and Van Driel proved the existence of propagating degrees of freedom on the boundary of the spacetime. Hence, studying the asymptotic nature of general relativity will elucidate properties of boundary gravitons. Therefore, it is worthless to study another boundary conditions to induce asymptotic Lifshitz symmetry and explore its consequences. So with the motivation defined, let us define right now our objective to pursue. We will study a simple Lifshitz invariant model, the 1+1 anisotropic chiral boson model. We are going to study the model, but in terms of fermionic variables, and we will define an electric charge operator and compute the two-terminal conductance as a consequence of the linear response of the theory. So now let us study the model. The action principle for the anisotropic chiral boson is the action principle that you can see here, where z is an odd integer, k a constant, and positive and negative signs are for left and right movers correspondingly. It is interesting to note that for z equals to 1, we obtain the case reported by Ferranini and Yakib. So let me talk about some symmetries. The action is not Lorentz invariant, but scales anisotropically. The action also is PT symmetry and has a U1 Kac-Moody symmetry. In Fourier space, they satisfy the following algebra. Also, the theory has a gauge symmetry, and the equations of motion are chiral, and also a total derivative. We can integrate in the position in x and obtain the equation of motion that you can see here. However, the integration constant the integration constant f of t was fixed to zero, and this is a consequence of gauge symmetry. Now, the solution of this equation is a wave superposition, and the dispersion relation is k powers to z. We can quantize the theory, and the Dirac bracket can be computed from the kinetic term as following in the blue term. So now we studied the model in terms of the bosonic nature that he has. Now we're going to study the same model, but in terms of fermionic variables. For this, we are going to define two fermionic fields, Ci and Cj, where I is different from j, and A and j are labeling the 1 to n particles. And we are going to define the annihilation operator C and the creation operator C dagger, where the dots denotes the normal order of operator O, where the bosonic field is expanded in some bosonic annihilation and creation operators respectively. So now we're going to use the Dirac bracket we found before. With that, it is possible to prove that for x different from x prime, the anti-commutation relations that you can see here satisfies. With this, it is possible to find the commutation relations of the bosonic creation and annihilation operators that you can see here. And then when we compute the operator product expansion using the Baker-Campbell-Hausdorff formula, we obtain an operator rho that's proportional to the spatial derivative of phi. And this operator rho is a bosonic quantum mechanical fermion density operator. Finally, using the conservation equation, we can find a quantum mechanical electric current operator I that is proportional to the time derivative of the bosonic field phi. So now we studied the theory, but in terms of fermionic variables, we are going to compute a two-terminal conductance associated to it. So we are going to consider a perturbation delta H, that is, it is defined as an integral of some external chemical potential mu times the quantum mechanical operator we found before, rho. Now we're going to apply the Kubo formula. The Kubo formula is a formula that allows us to compute the susceptibility of the theory at first order, where the brackets in red denotes the expectation value of these commutators. We can obtain the linear response of the perturbation defined as delta, expectation value of the quantum mechanical operator I, defined as the difference of the expectation value with the perturbation and minus without the perturbation. In frequency space after a Fourier transform, we will obtain the following susceptibility, where the function f can be computed using a standard complex analysis, and we'll have the following form, where in this case, I is the difference between the position and Kp are solutions of the following equation. Now we're going to consider an external electrostatic potential that produces a flow between the two reservoirs located at positions x less than xl and x greater than xr. And the chemical potential in frequency space will be given by the following expression here. Hence, the total current will be read as a huge expression that you can see here. However, it will be remarkably reduced when omega goes to 0 in order to obtain an Ohm's law where sigma is the two-terminal conductance, and it will depend of the K factor that was in the action principle and of the anisotropic exponent Z. So now we computed the two-terminal conductance of the anisotropic chiral boson theory, and now we are going to review some facts about ADS3 general relativity. In the vacuum and with negative cosmological constant, general relativity can be described in terms of two copies of the Chern-Simons action, where the Chern-Simons action is given by the following action principle, where the brackets denotes the trace in this case, and A is a one-form gauge field where the equations of motion reads as a zero curvature equation. The gauge field A is spanned in the Lie algebra J, where J denotes the two independent copies of the algebra SL2R, whose generators for the two copies are matrices L-1, L0, L1, and satisfies the following commutation relation. So now let us apply a gauge transformation to the gauge field. We are going to choose the gauge parameter H in a suitable way, and the component of the auxiliary connection A will depend only of time and the angle, and will be given as a particular case of the following boundary conditions, where these boundary conditions reflect a metric near the event horizon of a black hole. With these boundary conditions, and after a lot of work, in the sense that the theory will have a constraint, we will have to solve this constraint, we will have to replace this constraint in the action principle. That name is a Hamiltonian reduction, and it will be possible to obtain the same theory we obtained earlier, the anisotropic chiral boson action, but at the boundary right now. So let me conclude. For the Lifshitz invariant theory, the anisotropic chiral boson theory by means of fermionic variables, we constructed an electric charge operator. We used the Kubo formula. We obtained a two-terminal conductance of the theory that has an explicit dependence of the anisotropic exponent Z. This two-terminal conductance has a remarkably explicit, as I said, dependence of the anisotropic exponent Z. In the holographic side, we consider an ADS3 theory of general relativity, and we use a suitable set of boundary conditions for the gauge field. And after a Hamiltonian reduction, we obtain in the boundary the anisotropic chiral boson theory. Finally, the new perspective that three-dimensional general relativity has given us is now in the process of being interpreted. So that was my talk. Thank you very much. Can you hear me? I cannot hear it. I cannot hear nothing.
Sorry, I forget to unmute myself. I was thanking your nice talk and opening the question session because you allowed us to recover a couple of minutes. So that's appreciated. So are there any questions or comments? Maybe I have a comment. Okay, Francisco, go ahead.
Thank you, Mauro. Thank you, Kristiansen. Just a quick question. How would you go in and try to compute AC conductivity in this model?
Yes. Let me go to the slide. You want me to some details about the computation?
Yeah. Okay. Yeah. Maybe not. I mean, it's too long. Don't worry about it. I mean, you computed the zero frequency limit of the conductivity, right? I was just wondering how or if it was just possible to do the the finite frequency or at least
yes, for the finite frequency we obtain a closed expression, but it is indeed a huge expression anyway.
Okay. Oh, so it can be done. Okay.
Yes, indeed.
Okay. That's what I wanted to know. Thank you.
Other questions? No.
Sorry. The expression we obtain in the without taking the limit of omega goes to 0, it will be a sum. I don't know if that is a closed expression. I don't know if you're saying closed expression in that sense, but it will be a summation.
Yeah, no, that's okay. I was just wondering if it could be computed in principle, but apparently it
will be, as I said, it will be a huge expression anyway.
That's all right. Okay, thank you. Yeah, I got it.
Thank you, Francisco. Danilo?
Yes. Did you say graviton on the boundary? And if so, what do you mean by that? Thanks.
Because we are studying the nature of general relativity at the boundary of space-time, so it's like maybe an hypothesis in the sense that the dynamics at the boundary will be given of boundary gravitons at the boundary of the space-time. That was what I'm talking.
In 3 to 2, this is the question.
What? Sorry, I didn't heard well.
3 in the bulk, 2 in the boundary, even there. Okay.
Well, I will say the same. Maybe I don't understand your question well, but we are studying general relativity, so I hope at the boundary we will obtain the dynamics of some boundary gravitons. So I don't know. Sorry.
No, but it was is in general or is 2 + 1 dimensions. I mean. Okay, we can talk discuss later. Thank you.
Okay.